Hello everyone and welcome to today's session. In today's webinar, we will briefly introduce what is ground penetrating radar to you and also share with you what ProSec can offer when it comes down to selecting a GPR for your usage in the first half. In the second half, we will be discussing some of the common and many unique applications that GPR is used in the many industries. Hi, my name is Shen. I'll be the speaker for the first half of the webinar. My colleague Augustine will take over for the second half. We are both regional sales engineers stationed in Singapore in ProSec Asia office, and both of us have helped many customers with their applications on site. The recording of today's webinar, inclusive of the presentation, will be made available to everyone on demand. Do reach out to us if you wish to have copies of today's content. We estimate the webinar to complete within 45 minutes. After this 45 minutes, we will have a 15 minutes Q&A session that will be open to all attendees. Please feel free to click on the Q&A tab on the bottom of the screen to write us your questions along the webinar, and we'll have them answered for you at the end during the Q&A session. For those of you just joining us, welcome. Without further ado, let's start today's webinar. Right, so for myself, I'll be introducing a GPR, and then for the second half, Augustine will be discussing on the applications of the GPR. Right. So today we have four main topics. We will be covering the principle of GPR. We will be covering the live eco solution that ProSec can offer, and then we will go on to discuss about the two GPR equipment that ProSec can offer, and then the last one is some of the updates that we have to help users improve their user experience with a GPR. Right. So what is ground penetrating radar? So it's actually a geophysical method that uses radar pulses for subsurface imaging. So it actually uses radar to detect reflected signals from subsurface. So GPR can be used across a variety of channels. We can use it in rock, we can use it in civil engineering. As you can see on the slide, we can also go to, it can also be used on rock, soil, ice, pavement, and even structures. So what kind of defects or what kind of objects can it detect? It can actually, it is very, very sensitive to a metallic object. However, it can also detect voids and cracks if they are big enough. Right, so ground penetrating radar is used in these three core functions in the industry. We use it for SBU verification for inspectors to check on the building after they are built. Right, they want to verify the structures are built to the standard. The next one is integrity assessment. So it is used for engineering studios, used by engineering studios and investigation companies to maybe assess old buildings where they don't have any drawings to start with. So GPR is a good equipment for this kind of application or usage. And the last one is for use for heat prevention. So in the industry, I think many companies, they want to assess or even to check the compressive strength of the building, right? So they will need to call to extract core samples from buildings. So in order to extract all these cores without hitting a rebar, first a user has to detect all the rebar location before placing the rebar, before placing the coring equipment to core on the correct area. Right. So for a GPR component, it's actually very simple. First, we have the antenna. Second, we have the encoder. And with this, it is used to capture data and then eventually pass on to a data logger, in which case for ProSec, we are using an iPad as our data logger. So using iPad has its pros, right? So we have powerful probe together with powerful software, iPad. So we have intelligent software at our fingertips. So with this combination, we are able to perform many, many unique and special applications. So a very quick discussion, or maybe to share with you how actually GPR works in capturing a signal. So in this image that you see, this is a concrete structure, and then embedded inside the concrete structure there is a metal rebar. So the little device above is what we call a GPR. So as we move along the surface, right, it captures the reflected signal at every location where it moves. So when it starts to capture data at the first location, the radar that travels to the specimen takes a longer time to detect the signal, right? So it comes off as a longer time of flight duration. So in the actual data collected over at the right side, you will see a hyperbola kind of imaging that actually represents an image, for example, a rebar, right? So for GPR, it detects the amplitude, the reflected signal based on the amplitude, and the amplitude is very dependent on the dielectric constant between the materials. For example, concrete and metal, right? So GPR is very sensitive to metal, so you will get very good signal. Whereas maybe if embedded material is maybe PVC pipe, maybe you will not get a strong enough signal as what you get with a metallic object. Yeah, so what we have for POSEC GPRs, well, how we are different from the other GPRs in the market. So we are using a ultra wideband technology. We call it the step frequency continuous wave. What does this mean? In short, it's very simple. In the market, if you are getting a low frequency GPR, you are able to penetrate far, you can see far objects. But the thing is, you don't get good resolution near surface. On the other hand, if you get a high frequency, you get very good resolution on near surface object, but then you lose out on the penetration depth. So for users who wants to measure or detect objects from near surface to a very deep depth, right? They have to get 2 GPRs in the past. But for us, because we are using ultra wideband, for 1 GPR, you can expect very good resolution for near surface detection. At the same time, you don't lose out on the depth penetration. So over the years, GPR has evolved a lot. First, it came up with this when we collect data, this is the signal and the screen that you see, the data that you see. This is what we call the non-migrated B-scan. And over the years, and with the algorithms and softwares that we developed, right, we move on to having B-scan migrated view, which is more clear for an untrained operator, right? And then we move on to have tomography. We can use a time slice to check on the different depth to interpret rebars or data captured at different depths as per your requirement. And then for POSEC GPR, we also have this 3D imaging and augmented reality. So what does all this do? It helps to, it makes your interpretation simpler. So anyone with a GPR can perform a job with maybe 1-2 hours of training. So next, I will discuss, share with you our ecosystem of GPR. So as you know, mentioned earlier, our GPRs are wireless. So they are connected to an iPad screen via Wi-Fi. So with the iPad, data is collected from the probe to the iPad, and then they are stored into the cloud system. POSEC cloud system is free to use, and it has unlimited space for you to store your data. Right. And how can an iPad help you in real life scenario? So we have an iPad at work. Maybe myself, I'm doing an inspection work site, right? And then because I'm using iPad, I can have another buddy of mine or my colleague in the office, okay, connect to my iPad via TeamViewer, Zoom, Skype, any social media program to view my iPad. So in the office, I can have experts help me to interpret the data on site while I'm on site. What else? I can actually instantly share all this data to anyone in the world just with a Wi-Fi connection. I will share them the link, and then they can immediately go to the site to view the data or even download the data for their further usage. Right, so for GPR, the most common two techniques that we use is the line scan. So in this data, we actually went to Indonesia to do a scan on the bridge. Right, so as you can see on the image now, it's actually the non-migrated view. Okay, it's not so clear for maybe some untrained eye, but then look at this. This is the migrated view of the B-scan. Immediately you can see the arc on the bottom, whereas the arc where it shows the actual bridge condition, the arc on the bottom. And then the next one is, of course, the area scan, where most people use for coring application, for SBIL verification. Right, I will show you a video. So we actually went down to site. We had a customer asking us if we can help them to verify if there's any rebar structures in this column on site. So because the contractor that they use, they did not trust them completely. So we went down to site, we did a scan, and here's what we found. Yeah, so we went out to site, we completed the scan in less than 30 minutes, and immediately we are able to advise the contractor to double check this column, because from the scan, we are able to see a very small little hole near the center of the whole column. And eventually they hack out the column, and really that area is missing some rebars intended in the first place. Okay, so next we will move on. I'll move on to touch on the two model of GPRs that we have. So on the screen on the right top corner, we have the GP8000, and on the bottom, we have the GP8008, the smaller sibling. Okay, so as you can see, our instruments comes with no wire, it's totally wireless. And we built the equipment, we designed the instrument based on operator needs. We built it as ergonomical as we can. So as you can see, we have extension rod, we have accessories to help users do inspection. We have iPad holder to fix onto the GP8000 to make inspection easier for the operator. But on the other hand, if you see the competitor products in the market, right, some of them, the handles are blocking their screen. So the user has to maybe tilt left or even be in an awkward angle to look at the screen, right? And it's bulky. And on the bottom right, you can see the other instrument in the market, they have so many wires, right? So in the site, I think it is messy enough. We do not want our own cables to be part of the mess, to increase the mess. So ours, you can be assured that it's wireless. I mean, you can be, it will be tidy when you go to site. Yeah. So just comparison between the two GPRs. Why do we have these two GPRs? Can one do the job of in which the other can't? So if you look at the first 4 points, they are basically the same, right? They can both detect rebars, they can both detect post tension cables, they can detect other objects which are non-metallic too, right? And then we can also detect big voids. The thing is on the left side, the GP8000, because it comes with an ultra wide band from 0.2 to 4 gigahertz, it can actually penetrate to depth of near to 80 cm. Right. On the other hand, the smaller one, because its frequency is from 0.4 to 6 gigahertz, we actually tested, and then we found that it can be good up to 65 cm. The 50 cm here is because we tried on the real site condition, and we haven't had a case where we have tried 65 cm. right? And then for the GP8000, its additional features is that it has a live wire detection capability, right? So if in any case you want to check on a building that is existing, you want to do coring job, you want to make sure that you don't want to hit all these live wires also. So this will come very handy if that is the application that you're looking for, right? And then for the smaller GP8800 on the right, if you look at the last three points, because of its small physics, right, we can let it move on the curved surfaces. On the bottom right, you can see the photos over there, and it can also go into confined spaces. And then later on, we will also discuss a little bit about cross polarization, right? And then, of course, both of our GPRs, they have a fantastic resolution, and they are good for any coring jobs out there. Okay, a short video to introduce our GP8800. Just maybe take note of how easily you can switch the wheels from side to side. Right, for this video that you see towards the end, we actually went down to site. This customer had a problem. They did a coring job and they hit rebars in the column structure. Right, so we were asked to help. We brought down our GP8800 where it can fit into the small area that you can see over there. Right, so we did a scan for them and we found the rebar location as you can see on the screen right now. Right, so I'm not sure how or maybe what equipment that they use. Maybe their GPR is too bulky. They can't fit into this corner to inspect the whole column condition. Right, so in this case, the GP8800 will be a good choice of instrument to use. So in a way, both GP8000 and the GP8800 has their own purpose and unique applications. Right, so a little bit on what is cross polarization. Usually when we are doing a normal GPR scan, the object that we detect is usually perpendicular to the scan direction, right? Like this. So this is the only thing, or maybe most of the things you can detect. Okay, object that is perpendicular to your scan direction. However, when we are doing cross polarization, right, we tend to be able to detect objects that are parallel or even going along your scan direction like this. So with this, we are able to detect objects which are parallel. For example, if you are inspecting a rebar mesh, you can't see the maybe the horizontal rebar, so you will want to do a cross-polarized scan to look at the rebar. It is also very useful, okay, to see non-metallic objects. With cross-polarization, non-metallic objects tends to come out a little bit more obvious than metallic objects. Okay, so this is a scan that we did. As you can see on the top left, the non-migrated scan. It's the same scan at the same area, right? The normal scan and the cross-polarized scan. So for the normal scan, you're actually seeing the cross-sectional view of the rebars. So you can see all these hyperbolas on the screen, right? So they are actually rebars that are perpendicular to the scan axis. but you are not able to see the vertical the rebar over here. So all these are actually cross-sectional rebars, right? So for this, we did a scan from here to here. Over here in the screen, you're eventually able to see the rebar which is parallel to the scan direction. Also, you can actually see a little hint of indication of a perpendicular rebar location, right? Okay, so with this, I would like to maybe do a short demo. My colleague Augustine will be sharing with you a live demo to show you a live data to let you have an experience. Right, Augustine?
Yeah, so you can stop share the screen. Okay, perfect. So I'm Augustine. I'm going to give a lab demo how we talk about instant cross polarization. So the view is in the parallel direction with my testing direction. I can wirelessly trigger the measurement. So you can see the screen is collecting the data wirelessly instantly. So in this way, I do a normal scan. I can have a first layer, second layer. But in this way, I'm not able to look at the back wall clearly. Maybe I can do a second line scan over here. So you can see this data is collecting by a normal direction scan. So to keep it simple, we can just simply fold the view, as you can see, right? So I can get the scan at the same area. I will continue the measurement. So this way, when we do the scan, we call cross polarization. So you can see now the back wall become very clear. Did you see that? Just now I couldn't see the back wall, but first layer and second layer, which is perpendicular to my test location, is super clear, right? And for this line, why I can't see the back wall, right? For second line, because some a rebar along my measurement line is block the most of signal. So this is my lab demo. Thank you, Sung. Yes, Sung, you can continue.
Thank you, Augustine. Let me just go back to the slide. Okay, so in my last part of the presentation, I want to share with you what we have brought on board since we launched the GPR 2 years back. Okay, we have been doing a continuous improvement, and we want to make the user experience more and more better and better, right? Okay. Okay, so some updates. Yeah, so recently we brought a GPR Slice into our inventory. So GPR Slice is a very powerful software, which is used very widely in the industry by advanced users for them to interpret data, for them to filter results. Right. So with the GPR Slice, you can actually do customization or even editing to suit the scan contour. Right. You can also have imaging techniques. I mean, you can also see 3D display in the GPR Slice, right? And also you are able to see ISO surface interpretation for interpretation. So with all this, our GPR is compatible and is within our fleet of equipment that we can offer. Right. So for us, GPR is a one-stop solution. Right, so if there's any questions or if there's any requirement, please feel free to drop us an email and we will be glad to help you in the applications. Right, we can also help you to find out what is the best technique for your inspection. Okay, so for the second half of the presentation, my colleague Augustine will be sharing with you more on the very common applications that you see in the industry using GPR, and also some of the very more unique techniques that is less commonly seen. So Augustine, I'll pass it to you. Augustine, your mic.
Thank you, sir. Thank you, remind me. My name is Augustine. Thank you very much. I'm very honored to have the second session to share some past experience from our past work. Over here, I really, I have to say thank you to some of our partner, to my good customer. For example, MEK is our local leading specialist consultant. The full name called MEK Consulting. So they are in Singapore, is very professional and provide all this technical service on multiple specialists, including building material, chemistry, environment material, architecture, all these kind of different, including civil and structural engineer job. So in the past, we have a lot of interaction. We have some case study together. Not only MEK over here, also I will give some example from Indonesia, from Philippine customer, some from India, also including some result from Australia. So it will be a very interesting share session. And in future, I'd like to say, if you have some interesting work, I'd like to have this kind of interaction with you as well. So as a short introduction, so I think now all of us were staying at home, still performing our job. I really miss my workplace. I found this picture last night. I would like to share this picture so you can see. In the past, we do a lot of R&D job in this kind of new technique for this kind of AR. Did you see a rebar lift up from a testing test beside, right? So all this one, we will have some experience sharing later how we can use this kind of new technique. Before we really go ahead with some other application, I really want to have a short interaction with all the participants, right? Some of you visit our office, you may familiar with this small concrete block. So in this concrete block, we build with 3 rebar and 1 hollow pipe. And this is a very typical radar diagram at the right-hand side, right? Basically, we can see some rebar over here, right? Some GPR expert, you may easily interpret this data. But over here, I would like to have a short interaction with all of you. So the first question, maybe you can find this questionnaire for you to give us an answer, right? For the question, while the radar scan over on the rebar, right? The radar wave start from concrete surface until the rebar. Will the radar speed going faster or going slower? So thank you very much. Some of you already gave the answer. Yes, the radar speed will slow down easily. That's because the dielectric constant of the different material will determine the speed of the radar easily. Thank you. So I have a second question for you to answer. So the second question will be, what the radar speed when scanned in the concrete, right? So the subsurface of the concrete is the air. So the radar wave will go faster from the concrete surface to another air surface. Yes, some of you get the right answer. The radar speed will go up. It goes too faster. So from here, you can see exactly some difference from the radar polarity. For example, when we scan cross over the rebar and scan cross over the hollow pipe, right? So from this test result, you can see there's 3 rebar, 1, 2, 3. One of them I already marked as a rebar, right? So there's an interface from the concrete to air. And this interface is from concrete to rebar. So you can see 180 degree, this kind of inversion, right? So white, black, white, let's in POSEC data represent metallic object. So if you see black, white, black, then let's POSEC data represent a non-metallic object. So we can see from this radar raw data, yes, exactly. You can see 3 rebar and 1 of the hollow pipe. So you can see another thing is the hollow pipe and the back wall has a same polarity. So this just a small interaction with all of you, and some of you already know the result, especially who familiar with our system. So next one, to continue Sung's topic, how we use this POSEC GP 8800. I give some example. First one, really thank you for Taiwan partner Yan Shuang. Mr. Candy give this very fantastic result. So this is a hollow pipe, hollow column, right? So you can see a scan can be done from the inner curved surface or outer surface, right? At least a GP 8800, which is really suitable for this kind of curvature surface. So top, there's a raw data, below there's a McRae data. You can find the back wall. Of course, you can do a polarity measurement to get a better back wall reflection, right? So this is a measurement for first one. When we talk about column, and this data actually also provided by MAEK consulting company, and we go to the site together and we conduct some measurement. So I'd like to share this measurement. First of all, you can look at how we conduct this normal scan with a south view. And you can see the condition from the below is very worse, right? The concrete is intolerant. So this way how we live up for a vertical scan with a normal scan, and this is a test result. For example, we can look at the McRae view, there's a rebar layout from the first layer, and possible there's a below layer rebar layout, there's a total back wall. And next one is a B-scan image, which is a non-McRae view. We can see all this cross-section rebar very clear, even a rebar along the measurement line, right? So along the measurement direction, we also can see the rebar in our vertical scan. And this is a total penetration depth. And some of us already asked what's our penetration depth. Later we can continue this question. Just now beginning the video, we can notice is concrete very serious deterioration at the bottom of the column. At least a reflection may be present how is a concrete condition in the radar diagram, right? From left-hand side, it really give you an indication how bad is a concrete, especially we couldn't see the total reflection from the back wall. So this is something we can see from the radar diagram. So how about a cross-polarization measurement, right? So this is a cross-polarization measurement. So for example, we scan just instantly till you view 90 degrees, we can have this kind of measurement result. For example, over here, I can see a rebar super clear is a constant line, right? So this rebar definitely is along your measurement line. Of course, there's close to behind layer, there's another rebar over here, and a total thickness of the concrete. So this is a McRae view. I'd like to share another example, which is we do a scan in a horizontal direction. So left-hand side, there's a measurement with non-McRae. So both measurement is done in cross polarity. So first measurement was measured at the below of the column, and second measurement, upper one, is measured at the top of the column. So the result in non-McRae view, we can easily to see a first layer rebar, total thickness over here, right? You can see the total thickness reflection. Over here, I can see some beyond the column, there's a metal frame, including the metal banner, right? Let's some further reflection from the back. At least a Mac review. Now really go to our topic. I'd like to share some application from the past, including rebar scan, post-tensioning scan, defects, slab thickness. Also, we have some interesting content like the moisture content or coral content. Because the timing is really short, we have a few other applications to share in future. So now let's look at rebar. This data was done in China, Shanghai Concrete Research Center. Actually, there's a competition among different GPR manufacturer, and Porsche gave the best performance. So over here, there's 5 different sizes of rebar, from bigger to small, from left to right. The total slab thickness is about 15 cm. 5 cm is a first layer, and 10 cm depth, that's a second layer rebar. And you can look at the test result, right? So this kind of vertical resolution to present different kind of rebar per site, which is super performance. In terms, we have this step frequency continue with. It's too many examples when we talk about rebars, right? We have so many rebar scans in the past, but in this case, how about wet white mass? It's also common use for slab, right? To have a better performance at a single crack on the concrete surface. So in this case, after the result, we can easily project the result like an AR function. So you can see this rebar mass, how it looks like, right? Basically, this spacing only 5 cm. And mostly, I don't say which product, mostly for most GPR, for this kind of congested rebar mass, you may not penetrate or you may not have a further field reflection from the radar diagram. I'm interested to find something over this test result. I play a video how I interpret this result. So this result after the test, you just wrap on the screen, you can instantly have a 3D view. But over here, we can see the rebar mesh at the 5 cm depth. So we can further increase the time gain composition, which to amplify the further field object. So over here, I can find a clear pipe, right? So for this pipe, actually locate around 18 cm from the radar diagram. Also further increase some background removal filter, so we can see the rebar from surface much more clear and smooth. So over here, there's a pipe, and from before we do the small quiz, we know there's a metallic. So I talked to the building owner, they say there's a water pipe running below, there's a metal pipe. Over here, we can see a black, white, black, there's a total slab thickness. So total slab thickness after the dielectric constant calibration, so we can see it's about 27. So the first layer rebar is somewhere about 5 cm, right? So this is a test result for the first one. I'd like to share some example from the past how we do the post-tensioning slab measurement. So this kind of post-tensioning slab for buildings usage is huge, right? To increase the load, and you can see how the structure looks like. For example, for this kind of slab, we scan over. Actually, next example, we scan over from the beam to next beam location, and you can easily to see over the beam. There's another post-tensioning cable. And for this kind of congested rebar layout, it's not easy job for GPR to pick up all the details, but you can see how it's a super performance from Porsche instrument. So I leave up the two results, which is Mac review on top, non-Mac review at below, right? So you can see all the rebar from the non-magnetic view, right? There's a cover from the beam location. That's a first layer rebar, including second layer rebar. And for this case, actually, there's no top layer, only the bottom layer rebar below the post-tensioning cable. We can easily to see the spacing about this bigger hyperbola is about 1.5 meter spacing. Total is about 12 or 15 post-tensioning cable is located. Important, you can see as clear as possible this post-tensioning you can find under the rebar nest, right? And also possible you can find this kind of post-tensioning cable in between the two rebar mesh. So this result we collect in Singapore is I3 Research Center, and when we're doing the exhibition over there. So from this result, we can see first layer around 15 cm. This because this has a tau layer, a plaster layer, of course, increase the cover of the rebar. But we also can see a small interface around 10 cm, right? Then on top, there be some other facade material. Over here, we can see the whole geometry of this post-tensioning, which is along the measurement line. And important, we can have a second layer rebar and a total slab thickness about this measurement. We also have conduct some pipe location, right? Not only the post-tensioning. So this some example is talking about some conduits. This one was done in my hometown, right? As in China, Liaoning, Shenyang. So for this structure, actually I can zoom in, but we keep it short. First, we can look at the first layer rebar. The metal conduit is in between two rebar somewhere, and total slab thickness. Also somewhere you can possible to locate some second layer rebar, right? So this non-magnetic view. And now you can understand, right? So this similar polarity from white, black, white. So that's a metallic object. Metallic object in concrete, and easily we can identify as a rebar. Oh, this very famous block we use for our master training, right? And you see, maybe there's a Logas motorbike beside. So we can see there's a whole PVC pipe beside inside this irregular concrete slab. So we can see how is the test result over here. So we can see the hyperpolar polarity is totally different with just now the metallic pipe or metallic conduit. And it's exactly same polarity with a back wall, right, at 40 cm. So we can easily swap on the screen, have our macro view, all the full pack easily find the. You can do some fine tune on the gain, and later you can leave up your report easily. So this result for hollow pipe, either is metallic or non-metallic object. Oh, next one, also some interesting scan on this kind of hollow core slab. And this kind of hollow core slab is also commonly used for this kind of construction. You can see basically this kind of slab is built somewhere is more than 200 meters in a precast factory. And based on the building design, they will cut to required length. This is a test result, right? And you can see the hollow pipe location, you can see the rebar location. Interesting to find this kind of hollow pipe. Basically, hollow pipe is kind of pre-stressed slab. So for this result, actually has a two layer, right? On top layer has actually after construction of the hollow pipe is still pouring on a small thin layer of concrete pavement. So over here we can see interface from the non-magnetic view. We can see an interface. Let's refer to a small concrete cover, and in between there's a rebar. After that, there's a hollow pipe. So hollow pipe, we can have the reflector from air, right? Then give you a representation in the black, white, black, this kind of presentation. So this is a hollow pipe scan, first one. And can be another kind of hollow pipe. It uses a high density polyethylene, this kind of ball bag inside the concrete, not only to reduce the weight of the structure, but also give a lot some other advantage. So anti-noise, and for some seismic design, they also use this kind of. So actually this result was provided by Yan Shuang in Taiwan. It's also quite common to use this kind of structure design. I also make a video to see how this result looks like. So basically over here, I can see a clear reflector from the metallic, right? Let's refer to the rebar mass. And below here, there's a three hollow PE ball over there, right? Just beside the rebar, in between the spacing, and give you black white. This we use a signal total signal reflection we call envelope. We use a peak or envelope to locate the rebar location or object location. And you can see a 9 ball in this 60 by 60 area scan. And there's a rebar layout just beside the balls, right? So this example on hollow core slab or some hollow slab. Next example, I'd like to share some work before when we test or some data provided by our Italy partner PASI, or some result we together work with MEK, right? So this kind of monster wall. This wall design you can see from the brick disc is kind of header bond, a monster wall. So typically, this kind of wall is about 20 to 24 cm. This kind of thickness based on the brick wall, the brick disc length, right? So we can look at this data. Also quite interesting. You can see how the scan cross over the concrete wall horizontally, and beginning from around 2 meter to 3 meter, we have some signal loss. And later on, I process some, I use some additional built-in filter to find out, actually we still have a reflector from the total thickness, which correspond to later this reflector. And the problem from this 2 to 3 meter section actually has a higher moisture, I suspect for that. And we can see some reflector from the brick itself. That's I've like to say that's half of the brick, maybe the brick disc is broken in halfway, right? So overall, you can have this kind of GPR diagram to look at your data, analyze your data. So this is the first example. Second example is provided by MEK. We go to the site. This is a very famous building since 1901. So it's more than 100 years. So for this kind of historic building, how we conserve in future, we need to do NDT, this kind of investigation. It actually is showing in Sun Nanyang Memory Hall. So in this way, we already know some problem at the center wall. For the GPR radar diagram, really give evidence. For this wall, we know side wall is in dry condition, and this center wall in very wet condition. There's some material tests already carried on before. From there, we based on the material test, we know how is the moisture content. We know some other chemical content inside, right? For this test result, this macro review and non-macro review, I will go for step by step to explain further. So look at the first two sections. This is the first scan, we call M1. This is a marker 1, and this is a marker 2. I refer to this individual location we test. So you can see for this small wall at the side is a total thickness about 300, and we can easily use or find the back wall and do this kind of calibration. And we also can identify the thicker wall at center, which is 500 roughly. Take note why I say this dry wall, because dielectric constant based on our calibration only give you 7.2 as a dry condition monsory wall. And we look at marker 3 and marker 4, right? So first, radar diagram become very blurry, and secondly, the back wall become larger and a small back wall. So basically, we use a reflector from the small back wall and the larger back wall. We can calibrate the dielectric constant easily. It's almost 19. So you can see this kind of column, especially for historical buildings, is very important. How we can control for future, right? So we should consider, based on this kind of evidence, we can easily, instantly have this kind of data interpretation on site. This data also provided by MAK, we did together and Malay Conservation Center in Singapore. So in some monsory wall, we have some problem. We can easily see this salt crystal on the surface. So this kind of salt-related problem in brick monsory always cause some area can see some dark mark at certain height, or you can find some plaster chipping off from the surface. Of course, this will give structural deterioration or damage. So you can see the scan is start from here, right? Cross over the surface already took off. Just a short demo to, luckily I recall how Sung performed the measurement. So over here, I don't look at the front one. We can look at the back, right? As a very strong signal from the back wall. But in between, less because the coral content eating the radar energy. So in this way, actually, we don't have a good penetration, and our radar low data become very blurry. So in this way, we can easily identify the affect area from the radar scan. We just simply do a few vertical scan, horizontal scan. We can easily find out where's the real problem area. Next one, I will talk a little bit on our AR function, right? We have touched on AR function for quite long, since 2018. So we have this AR function embedded to our GPR inspection system. And some people really interest I'd like to say it's kind of joy when we do an AR scan. This result was provided by PCTE. So for concrete pavement, we can easily find this kind of serious crack. But what's the root cause? It can be some other cause. But for this particular case, the engineer, after interpret the data, especially project the AR image on the real test location, they can easily find this should be a joint concrete slab. So this reinforced joint was displacement, right? This kind of displacement of the rebar mesh as a real cause for this serious crack on the concrete pavement. So thank you very much. There's some data sharing along today's section about our application in the past, right? From the Sung's presentation, we also have a lot of interesting information. So before end our session, end of my session, I'd like to have a last question from all the participation, right? So for example, after today learning, so will you interest on our GPR? So you need us to contact you further, or you want contact us further, please help us vote your answer. Thank you very much. So same time, if you have any question, please leave your question in question and answer section. We have some expert behind to answer your question later. Okay, I will at least practice. Thank you very much.
Augustine, I think we got a very interesting question from Mr. Bimbao. Suppose the column size is 300 by 300 mm, I guess. Is it possible to do a scan, and what is the minimum dimension required for a GPR scan?
Oh, actually, we did a lot of this kind of, not saying 300 by 300, just for example, 200 by 1000. You can easily set up your scan from the screen now, because now our grid size is flexible. But maximum area can go is 60 meters for square meters. Yeah.
Yeah, so we actually have no limitation on the size that you want to measure. You can even go down to 100 by 100 also, we have no issue. And another one, for I think I think this question is asking about the color that he sees on our 3D image. Do you want to explain a little bit more? I think the color depth.
Oh, okay. Same time, Sun, can you explain the question at the same time? I try to find some example from my iPad.
Yeah, so when we are in this 3D image or even augmented reality, right, you can see different color on Augustine's screen right now, the purple, the cyan, and the yellow color. That actually we have recently added on as a feature of our GPR. They actually represents the different depth. So meaning you can have a total of 4 different colors. You can actually adjust them at different depths. So for example, you want 0 to 10 mm to be yellow. So maybe the first layer rebar will be a yellow color, and second layer rebar from 10 to 20 mm is set as purple. So you will have the second layer rebar as purple. So this is a better visualization for inspector out there, or have a better interpretation for their inspection. So obviously.
Okay, a moment. I've let to share my screen, and probably you can have a better look. So can you see my screen about my iPad? Yeah, okay. Yes. Okay, how about the color depth, right?
Yeah.
So basically we do a lot of this kind of area scan with a flexible area, and this maximum area just now I explained before. So you really can go to max area like 16 meters square. Of course, the far size a little bit big. In this way, maybe I can explain further. So we can lift up the cursor, look at this kind of, we call depth view or time slice view. You can look at the different layer, right? So in different depth. So of course, this are quite complex slab. We have a different layer of rebars. Of course, I can adjust the depth of the different color code, right? For example, I'm interested to look at the first layer in yellow color, and second layer in purple color, and later on is a blue color and light green color. So this is a result, right? Of course, if I know where's my test location, I can leave my AR marker Like I can scan on the AR map, instantly I can have this measurement result on the test location. I think some my screen is not clear now. Okay, I will reshare this. Okay, so as mentioned, you really can define yourself on the different depth with different colors. Yeah.
I think we also have a question from Mr. Pinky, but then this question is actually more, it's not directed at GPR. He is asking how confident is POSEC to define the actual diameter, actual rebar diameter. So I think for GPR, it is not the best instrument out there to detect the rebar diameter. Rebar diameter is actually using eddy current technology. And we have two instruments in our portfolio, which is the Profoscope and Profometer, which is able to give you an accurate cover depth, rebar diameter, and also, yeah. So it can actually determine the cover depth and rebar diameter for you. Okay, I think we have answered all of the questions from the floor. I think if you have any more questions, we can be reached at info-asia@screeningeagle.com. Please feel free to drop us an email in any applications that we can help. We will see you at the next seminar. Thank you.
Thank you.